Hi, thank you. Just a reminder, if you were not in my previous talk, I will speak in English because I just don't do talks in Russian, so I don't know all the technical terms you use. But you can ask questions in Russian later and we can talk. So this is a talk about the C++ and CLR memory model. And really, it's a talk about a bunch of different problems that you can run into when you write multi-threaded code and you don't use proper synchronization and you think you're clever enough to design your own synchronization mechanisms. And it's also a talk about how a lot of things we assume are only true on Intel processors, on x86 and x86-64. And once you port your code to any other CPU, pretty much any other CPU in existence today, such as ARM processors, which are iPhones and Androids, a lot of these assumptions break down, and your code isn't correct anymore. And the correctness issues can sometimes be really obvious, and like you run your code twice and it crashes, or it can be something that only comes up once in a million iterations, and then if you don't test your stuff really, really thoroughly, you probably will have production bugs. And now that you can use .NET and of course also C++ on a bunch of different platforms, not just Windows, not just Intel, I suspect it will be more important for a lot of developers. So that's why this talk. Now, I have a lot of information packed into these 50 minutes, so we might not have time to discuss everything. If not, the slides are up already if you'd like to review them. And also I'll be posting all the code, of course, that I use during the talk. So my assumptions: you are a C# or a C++ developer. Hopefully you can read code in both of these languages. You can write. You write multi-threaded code because we all do. You care about the correctness of your code. You want it to be correct across a bunch of different systems. And you're probably used again to Windows, to Intel, and you should also care about other platforms. What we'll talk about first is the concepts of atomicity, exclusivity, and ordering, which are three things that people often mix up, so I hope to clarify. We'll talk about what a memory model basically means, but again, most of this talk is not strictly about the memory model, but rather about issues that you will run into. We'll talk about a bunch of examples, and we'll also, along the way, understand what volatile does and what atomic variables are. Hopefully it's going to be interesting. And yep, this is some things here are quite advanced, and I'm not sure I understand them completely, but hopefully I understand them well enough to explain them. So let's start with these three fundamental concepts: atomicity, exclusivity, and ordering. So when we say an operation is atomic, at least for the purpose of this presentation, what we mean is that it is not interruptible. There can't be an interrupt in the middle of that operation. So a thread can't be switched out in the middle of the operation. The operation can't partially complete, like you're writing a value, so half the value was written and the other half wasn't written yet. On the hardware we are used to, on Intel 64-bit CPUs, you can assume that if you perform aligned reads and writes of values that are smaller than 64 bits, then that operation will be atomic. It is not interruptible, and there will be no partial results. So if you write an int, the whole int is going to be written out, no half int written, half int not written yet. And the problem is that even with this definition for Intel processors, a bunch of things we write in the higher level languages are not really atomic. And so the obvious example, which hopefully a lot of you are familiar with, is incrementing a variable. So plus something. If you do plus something, for example, in C++, a compiler might generate the code you see on the right, which is a perfectly valid sequence of instructions which reads the value from memory, adds 1, and then writes the value back to memory. And this is not an atomic operation under no definition. It's three different operations. Each operation is atomic. The whole sequence is, of course, not atomic. So again, hopefully this is kind of obvious and basic theory, but still it's important to understand that a lot of operations the compiler produces, even though they seem atomic at the higher level, language level, they're not really atomic if you look at the generated machine code. Even if you have an atomic operation, a single instruction which can't be interrupted, and there's no way for a partial result, the atomicity does not guarantee exclusive access to memory. So the atomicity does not imply exclusivity. If you have two cores executing an increment, right, just one instruction, which takes a value from memory, adds 1 to that value, a single instruction, it's atomic, non-interruptible, you still might run into a situation where on both cores, you only increment the value once. So what can happen is that both cores read 0 from memory into their cache. Both cores issue a write, which updates the value to 1, and that write is buffered in their private personal store buffer, and then one of these writes is going to win. So in memory, you will not see 2 updates, but only 1. The last to write will win. So just the fact an operation is atomic does not guarantee exclusive access to memory. So it's incorrect to assume that atomic operations are always thread safe, right? Atomicity is one thing, and safety or exclusivity is another thing. Now we can assert exclusive access to memory. We can tell the memory system that our core is going to update that value and no other core should be doing anything with that value. So on Intel processors, there is a prefix that you can apply to certain instructions. It's called lock. And what it used to do in the past is it would lock the memory bus. So basically, while you are executing this instruction, no other CPU would have access to memory at all. That's pretty expensive, but that's the cost of exclusivity. On modern systems, I think from Pentium 4, maybe even earlier, it's not locking the whole memory bus anymore. It's just making sure that cache line where your value is can't be in any other core's cache. So if I'm going to update it on my core, no other core can see that value temporarily. They just don't get access to that value for a while. That works, but again, it's expensive. And the more cores you have, the more expensive it can become. So that's exclusivity. We have instructions, explicit instructions, which tell the memory system, give me that thing exclusively, don't let other cores access it. That's the second axis I wanted to talk about. The third is ordering. And by ordering, I mean that various parts of the system, and we'll talk about that in detail, that's the main part of our presentation, some parts of the system might take the operations your application performs and reorder them. So they might take a write and perform it after a read, which was really before. Or they could take 2 writes to different variables and perform them in a different order. And the result, there's a bunch of different results, but one example result might be that my core thinks the value of some variable is 7, and another core thinks it's still 6. It hasn't seen the update yet. And then my core is operating based on some view of the world, which other cores don't have yet, even though I think they do. And a bunch of different issues can result. So we'll talk about some examples, hopefully, to make this more concrete. These 3 things, again, atomicity, exclusivity, and ordering, they do not have to be related. So if an operation is atomic, it does not guarantee exclusivity. If an operation is exclusive, it doesn't guarantee ordering. So these things really are unrelated on a lot of processors, including Intel. So memory ordering is the trickiest one, and the one that a lot of people aren't familiar with. So that's the one we're going to explore in some more detail. So there was this question which I kind of already answered. Does the processor, does the system, does the computer execute your program as you wrote it? Or does it just randomly reorder things around? So it turns out that yes, various parts of the system, the processor, the compiler, the memory controller, can reorder memory operations, move them around in memory, and it's an optimization. It's not a feature designed to test if you're really a very good developer. It's an optimization. So here's a few examples to just explain these are valid optimizations. So suppose you have this loop which reads values from an array, but there's a certain value which keeps coming back. You keep accessing data at P many times. So it would make sense for a compiler to take that read of data at P and just move it out of the loop, right? Make that read once and then reuse the value inside the loop. Compilers do that kind of stuff all the time. Now, we don't mind. This is probably going to speed our code up. We don't mind. Another example, which kind of links to something I talked about at the previous .next, is vectorization. So a lot of compilers today will automatically, for C++ anyway, will automatically generate different versions of loops which use vector instructions and vector registers in your CPU. So in a nutshell, the end result is, instead of, for example, adding and reading and writing values from one array and then another, one array and then another, you read 4 values from here and then 4 values from there. So basically there's some reordering of the reads and writes that you have. We don't mind that. It's an optimization. So that's good. Another example, this time a C# example, but again, it applies to all the languages. This is read elimination. So a compiler might decide it doesn't make sense to read a certain variable twice if it can read it once and cache the result. Again, we don't mind as long as it doesn't break our code. And that's a hypocritical position. We can't just assume the computer understands if it breaks our code or doesn't, if it breaks our intent or doesn't. So for example, if you build in C, in C++, in C#, queue implementation, a bounded queue, and somewhere you have this function enqueue, which puts a new element in the queue and then updates a variable called locked, puts 0 in there. And the computer decides to make it the other way around, to first update locked and then insert the element into the queue. You'd say this breaks your code and that's an invalid optimization and the computer shouldn't be allowed to do that. But it's the exact same thing as, hopefully, as the previous examples. The compiler maybe assumes that reordering certain reads and writes, as long as they appear unrelated, might speed some parts of your code up, and decides to do so. And in this particular case, it might totally break your intent, but that's just because you didn't tell the computer what your intent was. Now, why, again, would computers, so compilers, processors, perform these optimizations again? So one reason the processor itself would reorder certain memory operations is because of pipelining. So this very simple illustration shows that instructions inside the CPU pass through multiple stages. Now, this is a very simple pipeline, which might be true for a MIPS processor from 40 years ago. On modern Intel systems, there could be 20 phases like that. So an instruction moves between the phases. And while some instruction is in the first phase, another instruction might be in the third phase, and the third instruction might be in the second phase. So you could have multiple instructions at the same time in different phases. And the result, again, could be reordering. So you might have the first instruction here, for example, write a value into memory after the third instruction reads a value from memory, even though the third instruction was after the first one. So the fact there are multiple stages in an instruction's execution could lead to reorderings like that. Again, unless you tell the computer that you can't allow that to happen, that you have to have these instructions execute in the original order. And one final reason for these optimizations has to do with memory latency. Basically, the time it takes for updates to propagate all the way into the memory system. So on modern Intel processors, for example, each core has its own write buffer, which is a little queue which stores the most recent write operations that core performed. And that buffer is flushed into memory in the background. So your instruction says write X, and the CPU says done, but really it's just sitting in a buffer which no other processor can see, and it's flushed to memory asynchronously in the background. And then even once it is flushed out to memory, it has to go through multiple stages of cache, which again, the updates propagate rather slowly. Now, just to bring this down to earth, what kind of reorderings are permissible? What kind of things would the CPU perform? For example, would the CPU consider a valid optimization? So there is this one rule which says that data dependencies have to be honored. So for example, if you have a thread that writes 1 to the variable x, and then the same thread reads x, it's going to get 1. It can't not see the update it just performed. That's reasonable. Or if you have a thread write y, and then write x, and then calculate the sum of x and y, then I don't know if it's going to write x first or y first, but it's going to do both of these things before it's going to read x and y again. So certain basic obvious things must hold. But once you have multiple cores which access unrelated variables, pretty much nothing holds. So for example, on ARM processors, which is what you have in iPhones and Androids, most iPhones and Androids anyway, the CPU is allowed, according to the specification, to reorder any 2 pairs of accesses to memory. It is allowed to reorder reads and writes, writes and reads, and reorder writes among themselves. The only reason probably why we don't see this every day is that we don't use these very weak processors. We use the much stronger model which Intel hadn't had for a while, and under the Intel model, the only thing you might see coming from the processor, the only reordering from the processor that you will see is a store after load, which basically means if you have a write followed by a read, the CPU might, as an optimization, do the read first and then the write. So you had a write and a read, CPU does read and then write. That's the only thing Intel processors allow. Other systems might have other guarantees, and that's the painful part. It depends on your CPU. So here's a quick example of this. I have here in Xcode a very simple C++ snippet. Basically, there's this thread over here, which I run on multiple cores. So I basically create 2 of these threads. And what the thread does is 20 million times, right? It takes a lock, updates a shared counter, and then releases the lock. Seems pretty simple. Now, the lock implementation is up here, and that's actually the problem. But, you know, assume that someone else gave you this lock implementation and you trust them, and now you want to test the result. So here's an iPhone simulator, and I just run this thing and print the value at the end. So I run this thing on 2 threads. Each thread makes 20 million updates. The end result should be 40 million. Let's see. So I'm just going to run it again. Stop and run. Okay, it takes a little while, but we should see 40 million. Great, works. Now, the iOS simulator is running on my Mac. My Mac has an Intel processor. So let's run this on my iPhone. So I'm just changing the target to my iPhone, Valeria. Now you probably won't be able to see the screen, but I'm also printing the result to the output window. So you should be able to see it there in a few seconds. There we go. Close enough, but not 40 million. If you don't believe the output, here it is, right? It's not 40 million. Yeah. Okay. So, the lock is broken, and the lock is broken only on ARM. The lock works on Intel, the lock doesn't work on ARM. And as you see, it's not like it never works. It didn't work for one update out of 40 million. Pretty painful. I'll have one other example of that sort to show you a little later. Okay. So here's a few more practical examples for us to experiment with the notion of reordering and try to, figure out what we can do. So suppose you have this little piece of C or C++, this even works in C#, where one thread is checking a global variable to see if it's null, and then using that global variable. And the other thread, at the same time, is constructing a new object and putting that in the global variable. Now, reads and writes of pointers to memory are atomic, and it would seem that you have one thread writing, one thread reading, so you don't have multiple updates that can, disturb each other. So this just should work. But it turns out that on ARM, for example, this is actually broken. What can happen on ARM is that the constructor also performs writes, right? Every constructor probably initializes the object, so the constructor itself is performing writes to memory. So the writes performed by the constructor could actually be delayed and happen after the write to the global variable. So from thread 1's perspective, thread 1 will see an object which is partially initialized, an object whose constructor, in a way, didn't finish yet, even though the code is pretty clear. New widget, and then you assign the result to the global value, to the global variable. So on Intel, again, this would work just because Intel doesn't allow writes to be reordered, but on ARM, it would break. Much in the same way as the example with my lock just did. Example 2, again, this could be C# syntax if you want. So you have a pretty typical pattern. One thread is updating a variable and then setting a flag to true. And the other thread is checking the flag, and then if the flag is set, it's using the value. So hopefully you see it's the same thing, right? So the write of the value and the flag, they can be reordered. And if they are, the other thread might see complete, might see the flag as true, even though the value hasn't been written yet. Even worse, theoretically, on some platforms, what might happen in thread 2 is that the reads get reordered. So on some platforms, the CPU is allowed to speculate. It might read value first, and then check if the flag is true or not. And then, if it's true, great, we're going to use the value. If it's not, we're not. Again, if that happens, obviously, the result might be you use an uninitialized value. So this, again, might be broken on some platforms which have a weak model of reorderings, even though all the operations here are atomic and exclusive. You don't have two threads modifying the same piece of memory. So ordering is a real issue. My final example, which I'm going to run on Windows this time, and that again works in C# and C++, is Petersons Algorithm for synchronization. You might have heard about this thing in your operating systems class. It's really a very simplified version of that algorithm. So the basic idea is you have two threads, which want to enter a lock, enter a mutex, a critical section. So you have also two flags, flag 1 and flag 2 for each thread. And what the flag means, kind of, is I want this lock. So thread 1 says, I want this lock. So thread 1 puts 1 in flag 1. And thread 2 says, well, I also want the lock. So thread 2 says flag 2 is 1. And then they check the other flag, right? So I say, I want the lock, and then I check if you want the lock. Now, if we both want the lock at the same time, that's contention, right? So we just try again. We just back up, we set the flag back to 0, and we try the whole thing again. That's the go-to part in there. But if one of us saw 0, so basically I said I want the lock, and you didn't say you want the lock yet, then I get the lock. And if it's the other way around, then you get the lock. So this seems to work, like in principle. It's not very efficient, maybe, because we're just trying again and again, but it seems to be working, kind of. It's a polite exchange of opinions. I want the lock, you want the lock, and then we compromise. It turns out that on x86, even on Intel, this sequence is broken because the write and the read performed by each thread can be reordered. So what might happen is that I actually read your flag before I had the chance to set my flag. And then both of us might think the other one didn't want the lock when actually both of us did. So here's what it looks like in practice. This is not my code. It's actually taken from a blog post, which is referenced at the top of the sample. And what happens here is that we have two threads which access two variables. So the variables are here, x and y. That's flag 1 and flag 2 from my slide example. And I have both threads doing the following. So one thread writes x and then reads y, and the other thread writes y and then reads x. And we repeat this whole thing forever. Just repeat this transaction, and what we print out here is whenever both threads saw 0. So both threads thought the other one doesn't want the lock, and then both threads entered the lock, which is a serious problem if you have two threads entering a critical section at the same time. Now this is a C++ example, but the same thing works in C# as well, because again, Intel processors allow this reordering to occur, and the C#, the .NET memory model, which we'll come back to a little later, allows this to happen. Now let me run this thing just to show you it's compiled in debug mode. So there's no compiler optimizations, no compiler magic. Debug mode, 32-bit. Here it is running, and the issue is actually happening, and not very often, right? So again, the iPhone example was even more extreme, but even here, I'm just going to stop it now. After almost 300,000 repetitions, the bug only happened 14 times. So you might think that your synchronization algorithm is actually correct, because you tested it 100 times, you have some automatic tests which test it 1,000 times, and the bug just doesn't happen that often, so you don't see it. And even if you do see it, good luck reproducing it, if it only happens once in a few thousand repetitions. Now think about that kind of lock integrated into a larger program, and that particular little piece would be failing. That's very unpleasant. So this example, again, this Petersons algorithm, is one of the things we're trying to work against and fight and protect. So, a few words about the memory model, which is kind of the title of this talk, so I do have to tell you something about the memory model before we turn to how to protect our code against these phenomena. So there's this term coined a lot of years ago called sequential consistency, or SC. Now, we could do a whole talk about that, but it really is very boring. So the basic idea is sequential consistency means you can have multiple processors executing multiple threads, and the system has to make it so the results of the actual program are as if everything executed in program order. So you have reads and writes that your program is making. The system has to respect that. It is not allowed to do any reorderings. That's sequential consistency. And again, as we saw, reorderings, they don't happen because the system is evil. Reorderings are really optimizations. So sequential consistency prevents all these optimizations from being possible. Okay, so the next best thing, which is kind of what most languages use today, is called sequential consistency for data race-free programs. Again, it's very boring, the actual details, but the big picture is a race condition, a data race, is pretty much what you think. A data race happens when you have multiple threads, at least two, access a certain variable, access a memory location, and at least one of these threads is a writer. So you might have a writer and a reader, you might have three writers, but at least one of these threads has to be a writer. If your code does not prevent that, you have a race condition. So what SC-DRF means is that if you do not have race conditions, if you write your code in such a way that there are no race conditions, then the system gives you sequential consistency. Then everything will look as if it executed in program order. So you get the nice result of sequential consistency. That's what you get pretty much from the hardware today. That's what, for example, ARM offers you. If you take the necessary steps to guarantee you have no data races, the system will give you sequential consistency across multiple cores. That's all very boring and very theoretical. And still, it's kind of what the memory model is. So for C++, for example, as of C++ 11, our memory model is just basically SC-DRF. So C++, the language and the library, gives you the tools to get rid of race conditions. And if you don't have race conditions, then you are guaranteed by the C++ compiler, by the standard, that you will get sequential consistency. And you get pretty much the same thing from the official CLR model as well, from the official CLR specification, which is the ECMA specification, the European Association of Computer Manufacturers, ECMA. That's what you get from the official specification as well. If you take care of all your race conditions, you will get sequential consistency and no bugs. However, the current Microsoft implementation of .NET, of the CLR, offers you a little more. So basically, the current Microsoft implementation of the CLR gets rid of certain orderings which are not precluded by the official specification, by the ECMA specification. So basically, what Microsoft implemented is more friendly to developers than the ECMA specification. But still, even under the current Microsoft implementation, the example I just showed you with the Petersons X and Y would still be broken. You would still have to take care to avoid that data race, to get rid of that data race in your program, and only then you would get correct results. So again, hopefully you appreciate now why this talk is not really all about memory models, because it is not very exciting stuff. The exciting stuff is atomicity, exclusivity, and ordering, and how to get them, how to get rid of data races so your program is correct. So your program gets the benefits of the memory model. So hopefully, if you followed along until now, we'll see now how to get rid of these issues in your code. And that's a section titled Good Fences Make Good Neighbors. That's a pretty common English saying. Except by fences here, we don't mean fences between houses, we mean fences that the processor has to respect, which prevent certain operations from moving around in memory. So we'll start with the volatile keyword, which is a pretty common misconception. So in C++, the volatile keyword prevents the compiler from making certain kinds of reorderings. The compiler, please note, the compiler, and not the actual processor. Volatile in C++ has no effect on what the processor will do because the compiler doesn't just do anything special in terms of fences when you emit the volatile keyword. So if I just take this example here and make my X and Y volatile, again, this is the C++ version, and run this thing, we still get the reordering. You might think it's at a slower rate, but that's just a random piece of luck. We still get reorderings pretty much at the same rate as before. And of course, you don't have to believe me, you can check out the actual generated code. And the actual code, the assembly instructions that the compiler generates are the same, if you use volatile or not. Besides, I told you that I compile in debug mode, so compiler optimizations shouldn't have been the issue here in the first place. So in C++, volatile is pretty useless in terms of preventing the races we've been talking about. In C#, volatile variables are, for some reason, which is beyond me, but that's just the way it is, in C#, volatile variables actually prevent certain kinds of reorderings from taking place. What they do is introduce unidirectional, single-directional barriers, and I'll explain what barriers are, and we'll see what it means for them to be unidirectional. But basically, reasoning about volatile reads and writes is already quite hard, and it doesn't guarantee you don't have races. It doesn't guarantee that all reorderings cannot take place. So if you use volatile, you're still not safe. That's the simplest way I could put it. So let's take a look at a real barrier, a real fence, and where we would put it. So this is an example you might remember where one thread is initializing a global variable, the other thread is reading it and using that value if it wasn't null. So if you put a barrier in thread number 2 and the barrier prevents that write from being reordered with the constructor's operation, then we get the safety we wanted. So the memory barrier function that you see there, that's an actual function that you can use in C++ on Windows and Visual Studio. The .NET version of this is called thread.memoryBarrier. It's a static method of the thread class. And what it does is it prevents memory operations from moving across the barrier. That's the barrier or fence. Now, if you look at the actual concrete implementation, it just uses a specific CPU instruction, which the CPU recognizes and makes sure it wouldn't allow reorderings to occur across that point. Specifically on Intel, the only thing this barrier would have to worry about is if you have a store, a write, and then a read, so the barrier would have to prevent that write from happening after the read. That's really easy to prevent. So a barrier like that on an Intel processor is not actually a very, very expensive thing. On ARM, a barrier like that can be a lot more expensive. And if you just put barriers randomly across your whole code base, you might get very bad results. In our case, the barrier will help. So let me place the barrier strategically wherever I update my variable and then read the other thread's variable. In both threads, build and run. And you know, there is this saying that testing can prove the presence of bugs, but not their absence. So the fact we're not seeing any output doesn't mean our code is correct now. But you know, it obviously had some effect, right? It did something. No, but seriously, we have now prevented the CPU from being able to reorder these two operations, the write and the read. Okay, oops, didn't mean to blank the screen. So again, in C#, this thing is called thread.memory barrier. So that's just another example of using it. In the Petersons example, we place a memory barrier between the write and the read. Just one more example of using a barrier. There are also, and that's something I told you about volatile variables, we also have single direction barriers, which is very confusing, and as long as you understand the full barriers, you're okay for a lot of things. But it still sometimes makes sense to talk about one direction barriers as well. So the arrows should help here. Basically, a single direction barrier prevents reorderings in one direction. So if you take a look at the example on the left here, the monitor enter example, the monitor enter and monitor exit functions guarantee one direction of movement will be prevented. So operations after this barrier here would not be allowed to cross up. So basically stuff can't escape your lock and move out of the lock. And the same thing here. This barrier at the exit point is guaranteed to not allow operations to move downwards. So again, things inside the lock would not be allowed to escape and move outside the lock. In .NET, we have again single direction barriers whenever we access a volatile variable. Reading and writing a volatile variable produces a single directional barrier. Locks, such as the monitor, which is shown here, use single directional barriers, guarantee that there will be a single direction barrier. And there's a handful of other APIs where you are explicitly told this operation will introduce that kind of barrier. So now hopefully you understand what these barriers are. Now in C++, there is actually a fairly useful type called std atomic, which was introduced in C++, in the C++ 11 standard. And atomic variables give you full control over exactly what kind of barrier you're going to get. So let me go back to Xcode for a moment here and finally show you that spin lock code. So basically this is the implementation of a lock, which is based on a single flag, which is 0 or 1. And the current implementation of the lock and unlock methods uses atomic variables. It uses an atomic integer, which is 0 or 1. And I make it explicit what kind of ordering, what kind of barrier I would like. And I have two versions that I can use. So in one version, which is what we've been using now, both my instructions are using a relaxed memory order, which basically means there is no barrier, there is no fence at that point. Which basically means the following. If there is no fence in the lock function, and there is no fence in the unlock function, things can escape the lock. So writes performed under the lock can actually happen before or after the lock, which is not a very good lock, right? If it doesn't protect its contents. If I change this definition so that in the lock function I use a single directional barrier, and in the unlock function I use a single directional barrier, it's just the same thing as on the slide here on the left. It's a single directional barrier that prevents things from escaping in the right direction. So if I just make this change and run this on my iPhone, so it's going to launch now. I don't see it running yet. Coming up in just a second. There it is. It's running already. It's also a little slower, which is part of the cost. But we do get 40 million. And again, you might think, we have to run this more times to reproduce, but we could also look at the assembly and see that there are the necessary instructions which would guarantee to the CPU reordering cannot occur and that things cannot escape the lock anymore. So we have volatile, we have STD atomic, we have explicit full barriers. There's a bunch of tools that we can use to get rid of data races, to get rid of these ordering issues in our code. One final thing I want to show you before I move to one other example, with the final example I'll have today. One final thing I want to show you about barriers is that sometimes if you mix single directional barriers, you might actually not get what you think. So for example, if I made, in the Petersons example, if I make both flags volatile in C# or STD atomic in C++, I get single directional barriers for reads and writes. So for example, look on the left. The write here creates a single directional barrier going down, and the read, which I make here, creates a single directional barrier going up. Unfortunately, having both of these barriers there doesn't prevent the two instructions from swapping order. So making these flags atomic or volatile in C# wouldn't actually fix the ordering issue. Only placing a full barrier would. And this is tricky stuff, right? It's tricky to reason about, and it's tricky to think of all the options when you only have 2 threads and 2 variables. If you have more, it can be even a little more sophisticated than that. So you see here I have a button to skip to the end in case we don't have time for any of the bonus stuff. But I do want to show you one thing here, which is a thread-safe implementation of a singleton. I have about 4 minutes to do so, and I'll try my best. So I'll skip over real quick. We want to implement a singleton in C++ and make it thread-safe. So we start from something really naive, which obviously doesn't work because it's not thread safe at all. There's no protections. Multiple threads can initialize the singleton at the same time. This is broken. Fine. So we put a mutex around it, right? We put a lock around the initialization. We lock the lock, initialize the singleton, unlock the lock. This is unfortunately still broken because 2 threads could enter the lock and initialize the singleton. So we do the double check and lock pattern, which looks like this. I lock the mutex, and then I check again to make sure someone else hasn't initialized the variable yet, and only then I initialize it. This is still broken because we might have an exception during initialization, and then the mutex would remain locked, and we have deadlocked our whole process. Fine, so we use exception handling. That's not the interesting part. I use a class here which takes the lock in the constructor, releases it in the destructor. But this, and that's the important part, this is still broken for a reason we already saw. This is broken because the writes performed by the constructor can happen after the assignment to the singleton variable, the assignment to the pointer. So if the writes performed by the constructor are reordered with the write to the instance variable, another thread might check and see that instance isn't null and then use that object even though it hasn't been initialized. So you could say, okay, let's put volatile on this thing. Except in C++, again, volatile doesn't give you what you want because it doesn't prevent processor reorderings. So the only way to make this truly correct is to make the instance atomic, which would prevent the reorderings we wanted to prevent here. And I think the next thing I'm going to show you is a very good wrap-up for this whole session. This is how you can really do it in C++ today. This is how you get a thread-safe singleton in C++ 11. And this is supported as of Visual Studio 2015. You just put a static variable in a function, and the standard guarantees that this static variable is initialized exactly once, even if you have multiple threads accessing that function. So I think the conclusion would be, instead of trying to find curious and sophisticated ways around ordering atomicity and exclusivity, just try to rely on someone else. And indeed, my final slide is try to hide behind someone else's synchronization primitives. If you want to reason about atomicity, exclusivity, and ordering, hopefully I have given you a little things to think about, a few tools to do so, but really the best thing you can do is just use well-tested libraries which you know for sure take care of these issues for you. So we've run out of time. I will not take questions right now. If you would like to ask anything, I'll be here and outside, of course, for the rest of the day. I really appreciate you coming. Thank you very, very much. Thank you.